Here we have a similar situation that was done in class. We have a string connecting two objects. One is hanging vertically and it's not moving. And for that not to be moving, the object on the horizontal frictionless surface is rotating in a circle of radius half a meter, and what we need to do is determine what must be the speed of this object going around in the circle so that the tension in the string, which we're going to assume to be constant throughout the string, is sufficient enough to overcome, or sorry, not to overcome, but to support the weight of the 1.2 kilogram block. Okay, so let's go ahead and start this problem by drawing free body diagrams of each object. That's the way we always begin a force problem. Let's start with the hanging block. I'm going to call the hanging block M1, and the block on the circle, I'm going to call that M2. So the free body diagram for M1, let this be M1, we would have the tension in the string going upwards, tension up, and the weight, and I'll refer to that as weight 1. This figure is a little misleading because there is no acceleration, so the net force must be 0. These two force vectors should be the same size, so that's what it should be. Okay, so the tension must equal to the weight for M1. So if I were to write out Newton's second law, F net in the y direction, or the vertical, is what I would call the y, is equal to M1 times the acceleration of M1. Well, M1 is not accelerating, it's just being suspended there, that is 0. And the net force would be tension up minus weight, which should equal to 0. This means that the tension must equal to the weight of 1, which is, how do we find weight? M1 times G. Okay, so that must be the tension in the string. If the tension did not equal to the weight, then this block would accelerate downwards. If the tension was greater than the weight, then the M1 would be moving or accelerating upwards. But this is not the case, it's just being suspended or supported there. So that must be the tension in the string. So now if we were to take a look at M2 and draw the free body diagram for M2, this is what you would have. Here is M2. There would be naturally the weight of M2, the normal force from the table upwards. Now since M2 is not accelerating in the vertical direction, these two forces must have the same size. And then we have the tension in the string here. And this tension, the tension right here, this tension force is what's producing the centripetal force to keep the object in the circle. If the string were to snap, this object would just shoot off the table, right? So to keep it in a circle, there must be this force, which is the tension force, that keeps the object in a circle. All right, so we know what that tension must be. It must equal to the weight of block M1, okay? And these two must equal to each other, okay? Or else we would be accelerating. Good. So the net force on the puck, or M2, would be F net. We add up this force and that force, which are going to sum to 0. What we would left with is just the tension. So the net force is the tension, and this is responsible for the puck M2 acceleration, which is a centripetal acceleration because it's towards the center of the circle. Okay. So then the tension is equal to the mass of the puck, M2, and then we can rewrite the acceleration in terms of the speed, since that's what we're interested in, as v squared divided by r. Okay, and we know what this tension must be. We determined that to be the weight of the hanging object. So therefore, I will have tension, which is the mass of the puck, v squared over r. This tension must be the tension here must equal to the weight of M1. So this should equal to M1 times G. Okay. So let's find the speed now. So do a little bit of algebra. We would bring R up here, and then we would bring M2 down here. So V2 would equal to M1 G times R divided by M2 would give me V squared. Okay. So V, we take the square root, take the square root. V is equal to M1 over M2 times GR. Okay. Let's plug that into our calculators now to get it the right answer. So M1, which is the hanging mass, is 1.20 kilogram times G, 9.8 meters per second squared, times R, which is 0.5 meters, divided by M2, which is your 0.20 kilogram. So all we have to do is punch that correctly into our calculator, and that will determine what speed this object must be rotating so that the tension equal to the weight of the hanging mass. And that works out to be right around 5.4 meters per second. And that's how fast the pump must rotate in order to keep this hanging mass stationary.